morning, everyone.
Morning.
Morning. My name is Clint Panguhig. I will be your trainer for today. So we'll discussing about it's like an entry level of your current units. So I'll present to you the how to select and apply engineering design. So this is part of also of your course, the Advanced Diploma in Engineering. So I have a presentation here, but before anything else, if you need anything before we start our training, need coffee or Coca-Cola. So as part of the WHS or health and safety, especially here in Australia, so just in case if something wrong happen, we will have our assembly on the outside of this building. So you just go right and go to the main door. Then we have an assembly area there, just in case there's fire happening. And then we have toilets for the men. We have the left side, and then for the women is just on the other side of this hole here. So we're good. Everything is ready. So I already handed you all your resources, handbooks, and your assessment workbook. So if you have any question, just lift up your hands, and yeah, we can do this one as it's like an open conversation between me and the students. So here. All right, select and apply engineering. So before we start, I would like to ask anyone, how do you understand about engineering design? Do you have any, is anyone here the background of like doing some research of engineering design, especially in mechanical? No.
Backgrounds.
No.
Yeah,
Yeah.
I raise my hand.
All right. Do you have any idea?
Yeah, I have it. You are basically given, you'll be given by the client or the customer or your target group. You'll be given by your target group the required final output of any particular machine.
Yeah.
And based on that, you have to back calculate what are the, suppose you want to design a gearbox. So you'll be given an input speed and an output speed, and you'll be given an input power. You need to calculate what is the output power, and so based on that, you need to calculate various shaft diameters and what is the configuration of your gears inside the thing. That's what that is in the design. And so once you do the calculations of the design, then you come up with the gear diameters and the number of teeth where the gears are meshing each other. And so based on the number of teeth, you optimize the combination, the ratios, and you basically manufacture the gears. And based on the application and the amount of power that is basically generated by the gearbox, you'll have to decide on the material of construction of the gears. Once you decide on material of construction of the gears, you have to decide on the manufacturing method for the gears.
Yep.
Whether you're going to basically, cast the gears and then mill the gears, or are you going to basically forge the gears and then mill the gears, depending on the power requirement and the stress factor inside the material. You need to decide on those kind of material. So once that is done, you have already finished close to 80% of your design. And then once it is manufactured, you assemble the thing, you basically do the testing, inspection. Once it passes the thing, and you take measurements of the input power, output power, speed, and all that. Once you have done that, and you basically run the gear for, say, something like 10,000 hours, and if it stands up to that particular kind of number of hours, you have basically passed the design, and then you can now release the design for, as a standard product. So
It's good. Thank you, Celestia, for sharing your ideas, and we can cover up that one with this our lesson. So we'll check our overview first. So this unit provides mechanical engineering design theory for systematic planning design in a mechanical engineering context. So we will focus more on mechanical engineering design. So the module calls for work to be carried out as a design team, which will represent the design of mechanical and manufacturing engineering products, processes, system, and services using graphical techniques and an understanding of the specifications and documentations. So we'll cover all the manuals and CAD software. So later I will show you some CAD software models, like 3D models. So we'll contribute to the design process and the creation of models, graphics, documentation, specification, processes, and systems and services to support the design process. So planning and design will be implemented systematically with reference to the market and customers' requirements and the prevailing industrial environment design parameters such as performance, legal, resources, and scheduling will also be considered. So I think this is very like one of the most important thing. That's why we always come up with different designs because of our customers or client requirements. So I will show you one of a good example of like 3D here. I'll show you here. So I can see it on the video. So is anyone can recognize this engine? Anyone? So that's some miniature of combustion engine. All right. So that's a good example of like a production of like using CAD softwares. So carry on. So this is the purpose of this training. So we can see or we can learn the principles of mechanical engineering design. So in designing a machine, an engineer has to work out the size, shape, materials, and manufacturing processes in order to design a machine to perform its function without failure. So we are looking for something that's perfect. Nobody's perfect, but we're trying to make or to create a product that is perfect. So stresses, deflections, operating temperatures, and corrosion for each component and the overall assembly need to be considered. If there are no moving parts, then an engineer may only need to consider static loads, but depending on the size and shape of the component, environmental factors may need to be considered, such as wind loads, traffic, and earthquakes, etc. So we went to Gilmore Space yesterday, and we saw how they do their thing, like manufacturing the rocket, aerospace rocket. So you can see there that I just found out yesterday that the mainframe of the rocket is made up of aerospace grade aluminum or titanium. So it's not like an ordinary aluminum, but it's an aerospace grade aluminum. So carry on. So first, what is design? So I asked you earlier if you have any like ideas about engineering design. So engineering design is the systematic, intelligent generation and evaluation of specifications for artifacts whose form and function achieve stated objectives and satisfy specified constraints. So structured conceptual design. So this is the cycle from identify the problem. So we must identify the problem to avoid failures or any distraction to our design. So the second one, identify criteria and constraints. Brainstorm possible solutions. So most of, like, even in the design phase of a project, it takes years to, just for these three here, identify the problem, the constraints, and brainstorming possible solutions. So it takes time to, to follow this cycle. So the next one, generate ideas. That's why most of the companies have these different departments and function, because they are trying to give more information and ideas. So explore possibilities, select an approach, so build models or prototype, and then refine the design. So that's the cycle of the design process. And then next, engineering design process. The engineering design process involves a series of steps that lead to the development of a new product or system. So we have 8 steps here. So the first one, identify the problem, identify criteria, constraints, brainstorm. So you see that one earlier when I show you how the cycle goes. So the next one is the big idea. So we have our textbooks. I given you all the textbooks that we can make a reference out of it. So you need to have a balance of enthusiasm and practicality. It is all too easy to stifle the eagerness of a concept with the enormity of the project and equally. The lack of realism can overtake the due diligent process of preventing the individual, group, organization from making a commercial decision on the viability of a project. It is imperative that the feasibility of the project is analyzed from a number of perspectives before we even consider the manufacturability of a concept. So the Dyson vacuum cleaner is a good source of understanding on both positive and negative aspects of bringing something to market. So we have good example here. I'll show you. Yeah, Mr. James Dyson. So spent years designing different solutions to problems he saw, but all the designs he brought to market, the ability to actually make them was also a major consideration. The fact that he was not a formally trained engineer, but a graduate of art, has been attributed by many as the key to his success as well as his determination. So this is some of his inventions. So James Dyson is a British inventor. So before he came up with all of this design, there's lots of failures happening during the design, just the design. Even Thomas Edison, when he invented the incandescent electric light bulb. So just for the filament itself, it's 2,774 times failures.
No, 10,000.
10,000 just for the filament. Yeah. So that's how the design process works. So it's not really like it's just in one go, but you have a trial and error happening in the design. So we'll continue. So first steps to realization. So but before we start, I would like to show you one of like a YouTube video. This is one of I can tell that one of the perfect manufacturing of product. So we'll watch this video just to give you more inspiration.
Finish this one? You already done this one?
I think it's the same. Wait for your see. This one's really big.
How much will it take? Just reviewing. Yeah.
It's what
V2 engine.
As a non-native English speaker and writer, this is crucial for me. Grammarly's digital writing assistant helps 30 million people write more clearly and effectively every day, and that includes your boy.
Dashboard review and then words. Yeah. Ano pa ano dito?
Magkaroon ng constellation size
Yung sa
sa room selling.
deliver na ang mga circuit breaker. Kasi kami sa keyboard cooling sa basement.
Alright, so I will not finish that one because it's too long. So yeah, so we can see there that why Rolls-Royce is very expensive, right? Like because it's handcrafted productions, not just like all machines. So and also it's limited production and high level of customization. So so we go back to our topic. So all right. So the first step to realization. So you need to formalize a plan to end result. So the plan needs to take into account that you only have a concept that present, and you need to make room for errors and changes. So don't make too tight. If this is a planned process, consider a pilot plant. This is a smaller version of the real thing and will help highlight unforeseen issues that you could not envisage of the concept stage. So it's good to have room for errors, so you can distinguish or you can anticipate possible errors during the design. So keep going, we'll just make this one fast. So the second one, manufacturing. So we watched on the video how they how the process in the manufacturing. So keep going. So also Sadashian mentioned about the cost analysis earlier in the design, basic cost analysis to accounts for resources. Then basic presentation of the design. That's why tendering happen, or like the project proposal happening in the just a presentation. So also that one we have miniature there just to show you what the output of our product, and also engineering design drawings included. So I will show you one of engineering drawings we have.
What is BYM? What is BYM? Any idea? BYM. Bill of materials.
So we can see here how we build this combustion engine. So we have lots of components here, not only one components, but there's lots of components just for this single model. And then later on, for advanced, we can make like stress analysis, frame analysis, so dynamic simulation, just for us to know what's the error gonna occur on this 3D model. So it's a good example for this one. So we'll keep going. Okay, so that's included. So yeah, BOM is the bill of materials. So good example for this one is simply no substitute for big drawings with coffee stains in the site hut. We cannot bring our laptop all the time, especially if we are in the site in the site construction. So I think the copy of the BOM can interpret the drawings because we can see all the data on the BOM. So keep going, manufacturer of base, who and where. So it is normal to look for the nearest person to you in order to make a component. Starting with the base, you would look to timber shops local to you and start putting out tenders for manufacture and supply. Local might be quick but not be cheap, so that may push you to look further afield. So I'll show you good alternative of, like, you cannot get a lot, like for example Rolls Royce, they have very good quality or high level of materials they are using for the manufacturing. So I'll show you some alternative materials that we can use, especially just for the presentation purposes. So I saw this video. It's a bit funny how they customize or build or put together some materials here, but it's good. It's a good idea. See? So there's lots of like alternative we can use, especially in the design process of the product. We cannot use like expensive materials just to, in the conceptualization of a product. So it's good to know that we have like, what is more cheaper, or like we can talk about practicality in a project. So it's a good way of just to show the clients or to our colleagues what we can do to finish those products. So we'll keep going. So yeah, go back to this one, manufacturer or of base, who and where. So prior to this, if you are an internal facility, your own company's supply might need to engage in streamlining in order to meet cost constraints. So further to this, you may consider other materials. An ornate cast irons, mouse trap, or brass may be more expensive, but could be a premium alternative that changes considerations altogether. So it's a good way of like, even for example, especially if we're just studying, we're still on the feasibility study of the product. So keep going. Manufacture of metal components, who and where. Here is a common error. There are many levels of reinventing the wheels. CAD can be so quick that the designer often overlooks the fact that there may be a standard spring, clip, brackets, etc. available by the thousand for small changes. A quick search prior to letting a person on the virtual drafting board loose with the mouse and keyboard may be a useful cost saving, both in terms of design and time material. So as what I showed you earlier with our design, with our CAD drawing, so we can see, if we'll just make this one, it's like a wireframe. Yeah, so we can see all like common possible, or like you can see all the internal of our combustion engine. So we have all the piston inside, we have the propeller, and then if we will make this one more detailed, we can see all the components. So in this way we can, anticipate what we need to build the combustion engine. So go back to. So it's a good way of like, presentation, or showing our clients what our product look like, because we cannot build, this one. Just for this one is a bit expensive. Like you can buy this one on J-Car or maybe on other electronics shops, but it's too expensive, especially for the students. So we have lots of softwares, in the market for educational use. You can use Inventor or SolidWorks, or what else? AutoCAD, just to, for example, we have clients, we can present our products by using all the softwares. Yeah, it's a good way to learn softwares for our CAD. And then we'll continue. So assembly cost, who and where plus logistics. This goes back to basic assembly methods, but it is proving out of the work chart. Often it is simply done once and left to run to the term of the production run, but these days the continual revisiting of the assembly method is becoming the expected practice. the first tab, and it is always going to have room for improvement, so not only time savings should be looked for, but ergonomics and safety issues should be studied. So that's part of the design process, the assembly cost. Like for example, as what we have yesterday, that they will that they will travel, or that they will bring all the parts of the rockets to the north side of Australia. Yeah, Bowen. So it's a bit like, it's a risky. You need to consider the traffic, because it's a large part of the rocket. So all the safety, all the ergonomics, it should be considered, like the safety of the drivers, the safety of the public. There's we need to consider all the risks or hazard. Okay, we carry on. Packaging, who and where, plus logistics. From previous sections of this module, this may be outsourced or not, but packaging and shipping are an art form in engineering discipline, all of their own. If the product arrives looking thrown together, unprofessional, or even damaged in transit, the sale is lost. Although packaging is rarely kept, how it is delivered is often remembered. In site construction, before the excavation, all the excavation happening, you should consider where you can put all your materials, like from the cement, or from sand or rocks, because you cannot put that one in the middle of the project, because that's it should be ground zero, so where we can put all the footings or the foundation of the building. The same thing in mechanical engineering. We should always consider how we can arrange everything, so it will not cost us time, money. It should have that's the use of the engineering management. So we have to learn how to handle the project, or the production of the product. So mechanical design conclusion. So before we go to this conclusion, we will learn something from the previous videos that we watched. You learn something? Good? Yeah, so before we go to the conclusion, I would like to show you what's the possible, what could be disadvantage, or an impact to the public or to the user to a bad design. So I have some video here. I can show you what's gonna happen if we will have a bad design or a bad concept of a project or a product.
Final destination.
imagine the effect of bad designs, just the bad designs. Obviously, you can also consider the, you know, the natural impact of the environment, like for example, there's a tornado or typhoons like that. So we also give the earthquake, especially in Philippines. We have lots of earthquake. So yeah, it's good to learn the, you know, the principle and, you know, how we can simply select and apply the right materials, like for example that we have learned early yesterday in rockets. So we go to our conclusion. So mechanical design conclusion. So as what I have said, I given you our textbooks, so we can refer all those information to our textbooks. So finally, you should prepare a document that outlines whether the item has meet all its criteria prior to starting the production go button. The title of this document is varied, but it is amounts to a sign off in order to make it professional and hold water legally. It should be agreed and signed by all stakeholders. So that's where all the documents should be signed by all the stakeholders in the project. So there should be a room for critique and discussion, but the final form should be a definitive and comprehensive document that leaves no ambiguity on what is going to be made where, by whom, and what agreements are in place. So this final piece of presentation is possibly the most important, and it will allow others to highlight any areas that they have better viewpoint on that, the author of that document. It is not to be taken lightly, and probability should be done by more than one person, so all objectives can be looked at. So that's the important of a team, like team, how do you call that one? Working as a team, you know, we can put together all the ideas, what's the possible solution for a problem. Yeah, teamwork. Yeah. So yeah, there's lots of stakeholders, you know, involved in just a simple, like for example, this pen here, the whiteboard marker. Maybe I can imagine the, you know, the procedure, how they make this whiteboard marker. So maybe just for the design of this cup, maybe how many stakeholders or person. No, I don't like this kind of, like there's like vertical lines here. It should be soft like that, but you know, it came up with this one, this design. So there's lots of, you know, happening in the process of a design. So the industrial world of design is littered with case studies of this not being done diligently, and this is a whole other industrial sector employed to see who is to blame. So that's the very critical part, you know. It's like pointing, because this guy is, you know, approved the design of this piece of marker, so he's the one going to be blamed. But you know, that's the how we are trying to avoid. So the position of an industrial claims officer is a well-paid profession that decide who owes who and the end of a project due to delays, errors, missed deadlines, and overruns budget. So we try as, you know, as a future engineers, we'll try to get the best quality that we can do for our project, so we can avoid all the delays, error, missed deadlines, and overruns budget. So what do you think the reason why there's some delays, like, you know, errors or miss the deadlines? Do you have any idea what's some factors we can, you know, learn?
Maybe rate of delivery of the materials, something like that.
Yeah.
the logistic or something. So it's better maybe there's some factors and also the powers.
Yeah, that's true. That's very common with the big projects. Yeah, because sometimes it's shortage of materials, especially in the Philippines. Some of the what you call that one, the suppliers, they can just provide an amount of like materials, and also I can say like a poor communication, like poor coordination. Like for example, I will do some changes. For example, in the drawing, I will do some changes. Then without any communication to the other, like for example here in the structural, I will do some changes. Then without any emails, or I didn't tell the structural, mechanical, electrical, or even architectural. So that could result to misunderstanding. Then it could occur the errors. So yeah, that's very common. That's very common mistakes in a design process. So about this, in order to know how something is going to work or how much work it is going to deliver, you need to know how big or small it is going to be. So knowing it will fit and over a range of temperatures is another concern that has to be taken into consideration. There are so many things we need to measure in the literal sense, as well as the objective fit or purpose. So always consider this one, fit or purpose. Evaluation also, the term measure has a great meaning, many meanings. Of course, that is true in all walks of life, but here we are only concerned with the field of engineering. So that's the purpose of engineering. It's like, especially in mechanical designs, that's the purpose. That's why we are studying mechanical engineering so we can select, we can apply the right materials for our products. So, do you have any questions or clarifications or suggestions or objections? all the shons. So go back to so just to recap, just go back to our objectives. So I have some questions here. Now is the time to stop and ask the big questions. Thoroughly evaluate whether the idea ticks some, all, or more than the questions in the following list. Be hard on yourself. So is the idea really new or innovative? Yes. Some no. So whether it is new or not, it is substantially better to make it commercially viable. So as what we watched earlier about those invention, like what I can tell that that's not here in Australia. Maybe some of the part of the world.
Asian countries.
Yeah, maybe Asian countries. That's very common in Asian countries. Way back in Philippines, I saw a guy. He has a gun. It's like he's using like a big garter just to shoot the bird. Some of the people there are using those guns to do some hunting, like hunting some birds in the forest. So they use a big, like a large garter. They will just pull it. Then there's a hook here. They will put a stone. Then they can use like a slingshot. Slingshot. So how you call that one here in Australia?
That is, what do you call it? Huh?
Slingshot. It's like a
No.
letter C.
No, boomerang.
Boomerang. Yeah, it's a good. Yeah, it's like that's how they use here in Australia. So there's lots of alternative, but we cannot use that one commercially because there's a risk or hazard will occur, because that's just an alternative materials. But in engineering, we need to use the right materials, the appropriate materials for our product. So if it is simply a design of something done before a conveyor or example, does it meet the design criteria? So does it open you up to infringement of other people's design or work? So we need to consider all those stuff so we can get a safety, reliable, what else? Presentable. Also, that's part of the design, to be presentable. We cannot use like a $1 million project. We cannot use just like a very cheap materials. Yeah, we went to Gilmore Space yesterday, and we can see high quality materials there. We cannot see cheap materials, like even a single bolt. It should be in high quality, or it should be tested and measured properly. You can see on the other side there's like some machine there doing some vibration. So that's one of the good example of high quality materials. So everything should be tested, everything should be measured, just to avoid errors, to avoid mistakes in the design process of our product. So do you have any questions? Do you have any questions, Sebastian? No? Good. Thank you so much, everyone.
Thank you.
Thank you.
All right.
Oh.
Yeah, it's, I'm reading what I have to write.
What's that?
Have you-